Welcome, everyone. So today our speaker is Merlin Christ from Université de Paris, Rive Gauche, as far as I remember correctly. And we thank Merlin very much for his uh, uh, contribution to our seminar series. So uh, I'm now leaving to Merlin, and yeah, let's.
So let me share my screen. So yeah, thank you very much for the invitation. The goal of this talk will be to talk about complexes of stable infinity categories, let me say that this is will all be based on joint work with Tobias Dickerhoff and Tashi Walde. So the goal, I mean, is to first of all introduce what the complex of stable infinity categories is. That will be a categorification of a usual chain complex of, say, vector spaces. And second of all, maybe a way to construct examples of such complexes. And if you have, so how do you construct? Maybe we talk about this later, about the examples, how you construct them. So for this, I would like to start with the philosophy of categorification, or at least our philosophy. I mean, there's many different ways to categorification, but this is one of them. So we have classical concepts, and oh, no, that was it. Classical concepts and categorified concepts. And the way we pass from categorified to classical is by going to the Grothendieck group, K0. Grothendieck group. And so one concept we would like to categorify is an abelian group. And so for the categorification, I would like to propose to consider a stable infinity category. So if you're not very familiar with this notion, it's first of all an infinity category, meaning a category with not only morphisms, but also two morphisms, three morphisms, and so on, where all morphisms after level 1 are invertible. It's infinity category. And second of all, it's stable. So stable means that you should think of this as a kind of enhanced triangulated category. Enhanced triangulated. Because so if you have such an infinity category, you can forget about the higher structure and pass to the so-called homotopy category. And this will be a usual 1 category. And if you start with a stable infinity category, its homotopy 1 category will be triangulated. But having this infinity category and its infinity categorical structure can make many things about many failures of the theory of triangulated categories much nicer. So that's maybe one motivation to look at stable infinity categories. And for us, they will be a categorification of the notion of an abelian group. You go back by passing to the Grothendieck group. Okay. And to give also an example of a stable infinity category, you can look at the derived category of a commutative ring. The unbounded derived category. And so let's do another thing. So what's the categorification of the difference of 2 elements in an abelian group A? Well, for that, it's an interesting phenomenon happens. So you can't take the difference of 2 elements in a category. But what you can do is you can require there to be a morphism from X to Y, and then you can pass to the cone. So the cone of a morphism between X and Y, we also call this a cofiber. The cofiber. This is an element in A, and this is a good categorification of the difference. We'll see. This example will be relevant for later, but now we want to go in a bit of a different direction. namely ask for the categorification of a chain complex. Say a chain complex of abelian groups. So what would that be? That's a sequence of abelian groups, an minus 1, an minus 2, and so on, with a differential d, such that d squared is equal to 0. We all know this concept. And well, what we put on the right side, we call it a categorical complex. And let me give its definition. So definition. So a categorical complex is a sequence of stable infinity categories. So you start with curly an, then you have the differential to an minus 1, the differential to an minus 2. As you can see, I'm following the homological grading convention. This complex is required. So we want d squared. So what is d squared? D is a functor now, and d squared is also a functor, namely a functor from an to an minus 2. And we want this to be a zero object. So is a zero object. Namely, it's a zero object in this in the stable infinity category of functors. Stable infinity category of functors. So why am I saying it in this very precise way? The reason is that being a zero object, what does that actually mean? Well, so a zero object is an initial and terminal object. So you know what an initial object in a category is. It's an object where to any other object there exists a unique morphism. There's a corresponding notion in infinity categories of initial and terminal objects is an initial and terminal object. So terminal object. And what is important about being a zero object, that this is a property, not a structure. This is a property. So being a zero object is a property. And this means that in the definition of complex, of categorical complex, there is no, there are no, how do you say, no coherence data involved. There is no coherence data involved. So this is in big contrast in what when you say what a chain complex in a stable infinity category is, you need to have, well, a trivialization of d squared. So this is just some two morphism from d squared to 0, and then invertible two morphism. And then when you have all of these two morphisms, they need to be compatible in the sense of there being three morphisms, rendering certain composites as equivalent. And then there are four morphisms, five morphisms, and infinitely many levels of data. And it turns out that when you're looking at complexes just of, well, not in a, well, it is in an infinity category, but if it's in the infinity category of stable infinity categories, there is actually no coherence data involved. It is all unique up to contractible choice. And so we can use this naive definition of a chain complex in the categorical setup. And so let's do an example. So I should maybe also say we want these functors to be exact, plus exact functors. Okay, so let f from A to B be an exact functor between stable infinity categories. Then there are two examples of complexes So we can just consider the functor as a complex concentrated in 2 degrees. Okay, that's a trivial example. And another example would be to take, well, we can extend this 2-term complex to 4 terms by taking the fiber of F. You could also call this the kernel if you want. You take A, B, and then you pass to the quotient B mod A, which one can also call the cofiber of F. And then 0. And these are our complexes. Because, well, d squared is 0. And so this is so far the definition of a categorical complex. Now you could ask why do we want to study this concept, or what's the motivation for defining this? And there are interesting examples which one can study. That's maybe one answer. And another answer would be that, well, the eventual goal would be to categorify homological algebra. Categorify homological algebra. So this theory of categorified homological algebra, it's still conjectural in many parts, but some things we can do already, and some constructions. So we can categorify what an abelian group is. That's fine. What a chain complex is, and then what we will do today is also categorify how you totalize a multi-complex to get a chain complex back. And this can be used to construct interesting examples. And eventually this may be like the first steps in some interesting theory, which categorifies the usual homological algebra. Okay. So
can I ask a question?
Then let me yes, please.
Is this stable infinity category terminology, does it allow you to define homology of these complexes as an infinite category? Or?
I mean, yes, that's a very good question. Yeah, you can. I mean, the question is, what do you want homology to be? You can just take, as you see in this example here, you can just take the fiber and the cofiber, and then this would be the cycles, and these would be the chains modulo boundaries. You can of course say that's the definition, but that definition will be a little bit maybe it's not the right definition in general, because there's this example of a functor. So take any stable infinity category A, and then take the product with itself, and then you have the direct sum functor to A. This, if you take this functor, it's clearly surjective, so its cofiber is 0. But when you ask for the fiber, which elements are mapped to 0? Well, AB is mapped to A plus B. This is only 0 if both A and B are 0. So the fiber is also 0. Somehow, but this is not an example. Sorry, this is not an equivalence. So you now have an example of a functor which is not an equivalence, but whose naive homology is 0. So somehow there's, this is also kind of where we're stuck in the theory at the moment. And this example is maybe one of the main reasons. There's, if you think about naively about homology, you will get a notion or a concept which doesn't behave maybe well, or not at least similar to what you're used to with homology.
Thank you. Thank you.
Yeah. Okay, so the goal for today, let me formulate it as follows, is categorify the totalization of multi-complexes. Okay, and for that, we will start with a detour. First, something is wrong with the pen. Oh no, okay. detour. A detour on how to categorify the direct sum. Categorifying the direct sum. So let's continue with our table. Classical categorified. So a classical concept is the direct sum of two abelian groups. C is equivalent to A plus B. And what's special about the direct sum of abelian groups is that this is both a product and a coproduct. Right? So finite products coincide with finite coproducts. And this does not only work for abelian groups or more generally in abelian one categories, but even in additive one categories. So if you have an additive category, I will recall the definition in a moment. What products and coproducts coincide. And it turns out we can categorify both of these notions. So if we look back to the categorification of the difference, an interesting feature was that before we could just take the difference of two objects without any extra data, but when we categorify, we need there to be a morphism. And this morphism can be chosen to be 0, but it's more interesting to input maybe something non-zero. The same now happens when we categorify the direct sum. So we can have two stable infinity categories, A and B, and we also want an exact functor f from A to B. This functor, you can choose it to be 0, but you can also choose it to be something else. And then the direct sum is categorified by what we call the lax sum. I'll define it a bit later. And so, yeah, but it has this feature of, so if, let me say one thing, if f is a 0 functor, you just get the usual product of categories, and which is also then a coproduct. But there's more general datum which you can put in, similar to taking the cone. And so these direct sums live in additive one categories, and these lax sums, they live in what we call lax additive infinity 2 categories. Right. So I'll go a bit abstract now, but then we'll return to more concrete constructions after that. This abstract interlude is supposed to convince you that there exists a nice general theory, and then afterwards we'll see that there are actually concrete examples. So recall the following definition: a one category C is called additive if, well, two things are satisfied. Firstly, C is enriched in abelian groups. And secondly, C admits finite products. And if this is satisfied, then there's a theorem that in this case, C admits finite products and finite products. Okay, C, let's say coproducts. It doesn't matter here if you write products or coproducts. So let's say coproduct. Then C admits finite products, and these coincide inside with coproducts. And this is what we call the direct sum. So this is a very classical context, which I hope is familiar to most of you. And there's this will probably be the most difficult part of this talk. After I promise it will get easier. So let me tell you what a Lax additive infinity 2 category is. So an infinity 2 category, think of it as well, it's a category with all levels of morphisms, but only the 3 morphisms and above are required to be invertible. So there can be morphisms and 2 morphisms, and the 2 morphisms don't have to be invertible. So an infinity 2 category C is called Lax additive if firstly C is enriched in, so what was the categorification of abelian groups? I hope you remember. It was stable infinity categories. So you want C to be enriched in stable infinity categories. So this means if you have the Hom infinity category, C between 2 objects A and B, this will be is stable. So if you have an infinity 2 category, it will always have an Hom infinity category, but being that this is stable is the property, or the condition. And property 2 is that each diagram, so this is now generalizing finite coproducts. So if we take a diagram in C, where this is a small infinity category, this admits a Lax colimit. So a Lax colimit, this is a 2 categorical notion of colimit. Let me briefly illustrate what this means. So this is roughly the universal Lax cone. So what is a Lax cone? It's a cone where you have, say this is S, and then we have the cone tip, and then we don't, a Lax cone is a diagram like this, which does not commute, but where there is some non-invertible natural transformations, or non-invertible two-morphism. So it's a 2 categorical Lax version of a usual colimit, and if S was actually discrete, so just say S is the disjoint union of some points, then the Lax colimit is just the coproduct. So as a special case, finite coproducts are Lax colimits, but Lax colimits are a bit more general. And then the theorem, which we prove, is that the standard result about 1 categories categorifies in the setup if C is Lax additive, then the Lax limit of any diagram exists and coincides with the Lax colimit. And so we will apply, or this result will be for us relevant in the context where this infinity 2 category is for us the infinity 2 category of infinity categories, infinity 2 category of presentable and stable. Presentable and stable infinity categories is Lax additive. So if the term presentable, it's a technical term, don't worry about it. The point is that if we look at the category of stable infinity categories, this forms not only an infinity category, but actually an infinity 2 category. And in there, the categorification of the direct sum is the Lax limit, which coincides with the Lax colimit. And I'll now make this concrete. So what is, what is, no, that was not intended. Wait, okay, that was, Zoom is messing. Oh, well, this is by Zoom. Let's just write around it. What is the like sum? Sum. It's fairly concrete construction. So we consider the functor f from A to B as a diagram from, well, the category with two objects, 0 and 1. This is the one simplex, if you know this language, into this infinity category, into this category of infinity categories mentioned above. And then A plus FB is the Lex limit of F. And concretely, this means it has, what's an object? So an object is a triple, A, B, eta, where A is in A, B is in B. So if that was all we had, if objects were just an A and a B and B, then this would be the product. The product of two categories has objects just tuples. But then we have this additional information eta, which is a morphism from f of A to B in B. So somehow think of it, so if the morphism f was 0, the objects are thus the same as in the product, but here we somehow glue together A and B along this functor f into this like sum. And then, so morphisms are what you would expect. Morphisms. So if we go from A, B, eta to A prime, B prime, eta prime, this is the same as, first of all, a morphism alpha from A to A prime in A. And secondly, a diagram where you take f of A, go with eta to B, then you take f of alpha, go to f of A prime, then you go with eta prime to B prime, and here you have some morphism, and this is required to commute. So that would be the datum of a morphism in this category. And so if you know, let me make a remark. This category AFB, this has a semi-orthogonal decomposition. Orthogonal decomposition. A and B with gluing functor F. So these categories with semi-orthogonal decompositions, they appear in many contexts, for instance, in derived algebraic geometry. And it turns out that whenever you have such a semi-orthogonal decomposition, or a better version of a semi-orthogonal decomposition is a récollement. If you have that, your category is actually under some maybe technical conditions given as the Lax sum of the gluing functor. So these Lax sums appear very naturally in many contexts, but it's nice to see that this property of having a semi-orthogonal decomposition, it's actually a universal two-categorical universal property. That's maybe an interesting takeaway. Let me try to get rid of this. No, I don't know how to get rid of the annotation, which I mean in Zoom. Okay. Well, we'll just ignore it. Okay. So let's do an example, make this even more concrete. If you choose f to be the identity functor from d of k to d of k. So this is maybe the first non-zero functor which you can think of. then what is its Lax limit? This will just be the derived category of, well, so what is it? We have two elements, A and B. So A would be in the derived category of K, B would be in the derived category of K. And then we have a morphism from, well, f of A, which is just A to B. So what we're having is two elements in B of K plus a morphism from one to the other. And this is the same as a representation of the A2 quiver. Representation of A2 quiver. Yeah. Right. So that's maybe one concrete example. And what I should maybe also tell you is what the Lax cone is of this direct sum, because I claimed this is the model for the this is the concrete description of the Lax limit. So we should be able to write down this universal cone, and this looks as follows. So a Lax limit cone is a cone of this form. And the natural transformation going like this. And so this functor will map A, B, eta to, well, A. This maps A, B, eta to B. This is F. And so this natural transformation, it corresponds to a map from F of A to B. And this is just eta. So yeah, it's very easy to write down this this Lax limit, this Lax cone, and it is universal as it turns out. And maybe what is the Lax colimit cone? There we would have, this looks as follows. We have F going from A to B. Here we have the direct sum. And the morphism goes like this. And here, A, B, eta, it is mapped to 0, B, 0. And here, A, sorry, this is just B. And here, A maps to A, F of A, the identity on F of A. And then this natural transformation, it is just the map from 0, F of A, 0 to 0, to A, F of A identity, which is the identity on the second component. The second component of the triples, but otherwise 0. So that would be the Lax colimit cone. And yeah, that tells us this concludes this interlude on how to categorify the direct sum. And the remaining 15 minutes I would like to use to explain how to categorify totalization. But before that, I should maybe ask if there are some questions.
Just a simple question. This direct sum with F in the last version, this corresponds to a pullback diagram, right? If we had the non-categorified version over the map from A to B, right? My question is actually in the definition, we want the diagrams to strictly commute, right?
You mean this here, or what do you mean?
In the previous one, when you had F alpha to B, F A prime to B prime, so there will be a second morphism from B to B prime as part of the structure, and you want this diagram strictly commute.
I mean, there's no notion of, I mean, we're in an infinity category. there's somehow no good notion of strictly commute. But what we have is I mean, how you set up this infinity categorically, this then works with simplices. So you would have a two simplex here and another two simplex here. And the two simplex essentially expresses an equivalence between the composite and the diagonal map. So this would be these questions of strictly commuting or not, would all be dealt with in the infinity categorical machinery. And this is, of course, not a definition. You can't define an infinity category by saying these are the objects and these are the morphisms, because there's all the higher structure, which you can't define in this way. This is an illustration of what the objects and morphisms in this infinity category look like.
So do we know that Lax limits are stable infinity categories? That's like, is it part of the Lax limit definition that you will always get stable infinity categories?
Yeah, we're taking the Lax limit in the infinity category of stable infinity categories. So because it lives in this category, it's automatically stable. But there's one way to define it as a pullback. So you can say you take you have A, this goes to B, F, and then here you take functors from 0 to 1 to B, and then this would be the evaluation at 0, and then if you take the pullback, this is your Lax sum. And this is the usual, well, it's not a two categorical pullback, but a infinity one categorical pullback. So that's another way to maybe concretely define the Lax sum.
Thank you very much.
Thank you for the question. Any other questions? Last chance before at the end. Okay, then back to the categorified totalization. Okay, and first let me recall, so that we all have it in our head, what the usual totalization is. So given a commutative square of abelian groups, so A, F, B, C, G, D, G prime, F prime. And such a square of abelian groups is actually a special case of a bicomplex. So that's a chain complex in two directions, right? Here there's no all horizontal morphisms. If you compose any two horizontal morphisms, you get 0 because there's only really one. Okay. So how do you totalize? Its totalization is the chain complex. So we have 0. This goes into A. This goes into C plus B. This goes into D, and then 0, and so on. So what was the rule again? So basically, you take you sum over the diagonals. This is a finite bicomplex, so there's no ambiguity between taking products or coproducts over the diagonals. So that's how you get this. And then what's the differential? So here, this is just the map G comma F, and this would be the map minus F prime G prime. And why is that a complex? So what do we have to check? We have to check that D squared is equal to 0. So D squared, this is minus F prime G plus G prime F, and that is 0 by the commutativity of the square. So I hope that that context is also familiar to the audience. So next, we would like to categorify this, and there's two versions of categorification. So the first is the product totalization. So we start with maybe I write this. To move this a little bit down. So let A, F, B, C, D, G, G prime, F prime. So be a commutative diagram of stable infinity categories. So when I say commutative, I again mean in the infinity categorical sense. So we can define, and we denote this by A star, this square. So the product totalizations, which we write tot cross of A star. So, and we define it in a similar way as the usual one, right? We know how to categorify the direct sum. So we should put here some kind of Lex limit. And we put here a slightly different version to the Lex limit before, which is, it turns out it's equivalent to this Lex, to the Lex sum F prime right adjoint G, B, if F prime has right adjoint F prime R. So I'll give you a definition now, and this definition is equivalent to this one as a Lax bilimit if the functor F prime has a right adjoint, which it will have in most cases, but that's maybe a technical question. So there's a good definition, but the intuitive definition that is that this consists of triples C, B, eta, where C is in C, B is in B, and eta is a map from F prime of C. Let me maybe, I need some more space. So eta is a map from F prime of C to G prime of B. So this time we're not gluing along a functor, but we're gluing along two functors which target the same category. And we're saying we're adjoining a morphism not from C to B, but we're joining a morphism in D from the images of C and B. So that will again give you a definition of a stable infinity category. And then this is what we would put in this product totalization. And let me tell you what the differential does. So here, I'll only tell you an object. So A would be mapped to G of A, F of A, and then eta is the equivalence expressing the commutativity of the diagram, right? Because F prime of G is equivalent to G prime of F of A. And then the other differential maps CB eta to the cone of eta. And then the fact that D squared is equal to 0, this means that the cone of an equivalence is 0, which is, if anyone who knows triangulated categories will know this to be true, that the cone of an equivalence is a 0 object. So that's the product totalization. Next, I'll briefly mention that there is a dual notion. So coproduct totalization. This is formally dual. We denote this as follows. Totalization of A star. This is the chain complex where we glue C and B along A in some way. And I won't tell you what how to construct this, but maybe that this is C plus B glued along the functor GF right adjoint if F has a right adjoint FR. So let's end with a concrete example of this totalization construction coming from algebraic geometry. I am supposed to end at 50, right? Yes, okay. so we'll end right on time.
Can I ask you a question?
Oh yeah, okay.
What's the relevance of having this right adjoints? Like you could define it without having a right adjoint, but then there will be these products in the right adjoint. I don't even see if you replace F prime with the right adjoint, you will still have a commuting diagram. But so
no,
what's
that's
the relevance?
not, I mean, yeah. So the okay. So if F has a right adjoint, so we have this usual the diagram before CD, and then if it has a right adjoint and F prime also, then you can form this diagram. F prime right adjoint CD, but then this doesn't have to commute. This is if this square is if you have a commutative square and you pass only two right adjoints on one of the directions, this does not have to commute. If it does, so there's a natural transformation from this composite to this, and if this is an equivalence, well, we call this a Beck-Chevalier square. This is there's some condition on a mate, two categorical mate being an equivalence. Does not always commute. Not always commute. But here in this example, if you look at eta, it's a map from F prime of C to G prime of B. Well, this is the same as a map from F to F prime right adjoint G prime of B, which looks very similar to our definition from earlier, where we just adjoined a morphism from one object to another object, a functor applied to another object. So that's maybe that's kind of why you need the adjoint to transpose this natural this morphism to another morphism.
Okay, thank you. Thanks.
Yeah.
I understand.
You're welcome. Okay. So no, that's not what I wanted. I want this. Okay. So yeah, example. Let Z be a smooth scheme. Smooth scheme over a field K of characteristic 0, and D is a union of two smooth divisors, a normal cross, which are normal crossing. So normal crossing divisor. So this would mean that D1 and D2 are smooth, and their intersection is smooth of the expected dimension. And then we get a cubical diagram of schemes. Cubical diagram. D1 intersected D2. This goes to D1 schemes. This goes to D2. And this goes to Z. And then we can pass to quasi-coherent sheaves and get a diagram of stable infinity categories. So we get what we maybe call quasi-coherent of D star, where we take quasi-coherent sheaves on D1 intersected D2. Then we take the direct image functor to quasi-coherent sheaves. So when I write QCO, I mean the derived category of quasi-coherent sheaves. That's maybe standard in the derived algebraic geometry literature. That's why I think it's okay to stable. Okay, and then so actually it turns out that so you have this functor f and g and f prime and g prime, and base change. The base change theorem implies that G composed with F right adjoint is equivalent to F prime composed with G prime right adjoint. Sorry, that's something wrong. F prime right adjoint composed with G. So this question of being of having an of being able to flip one edge in the square and still getting a commutative diagram, this can be positively answered in the setup because of base change. And so then we prove that if you have this Berk-Chevalier condition or the space change condition, then the product and the coproduct totalization coincide. By base change or by Berk-Chevalier condition, that QCO of D star, this is so that we have two different versions of the totalization, but in this example they're the same. And yeah, we can give this a name. We call this is now complex. How does it look? So we would have 0 going into QCO of D1 intersected D2, and then into some QCO D1, some like sum of QCO D2, and this goes into QCO of Z. We call it the categorical intersection complex. Categorical intersection complex. And there are many interesting things to say about this complex. What kind of properties it has. Maybe let me just make one brief indication of this. So interesting properties. For instance, in relation to mirror symmetry. Relation to mirror symmetry. Homological mirror symmetry, that is. So there's another complex which you can construct using Fukaya categories, and then these two are equivalent. So you get a version of mirror symmetry which is not an equivalence between two categories, but instead between two categorical complexes. And final remark is that there's also an analog of the totalization in this example for higher cubes, where you basically iteratively totalize. Iterative totalization at adjacent coordinates. So if you have, for instance, if you have a 3 cube, you can first totalize, you pick two faces which are opposite to another, then you totalize them. And then what you get is it won't be a square, but it will be a bicomplex, and then you totalize the bicomplex. So by iteratively totalizing, you can get from from multi-complexes to complexes, and the story works similar in that setting. So yeah, that would be all I wanted to tell you today. Thank you. Sorry for going 3 minutes over time. I hope it's okay. And yeah, thank you for listening.
Oh, thank you very much, Merlin. It was a very nice talk. So let's take our speaker. So I would like to say any questions or comments. So maybe I will ask one thing about when you started your talk, you said that we categorify classical mathematical objects like Abelian groups in the categorified language to stable infinite categories and so on. So I will ask one question. This may be a very crazy question, but for example, can one categorize, I don't know, automorphic forms, for example?
I don't know. I would first say that I don't know enough about automorphic forms in the first place, and then secondly that it's not clear. I mean,
Or maybe the notion of, I don't know, how shall I say, group representation. I think
yeah.
one categorifies them because groups act on categories and so on.
Yes, you can do that. You can also ask for, I think the correct setting is Frobenius categories acting on other categories.
Right.
So there's a categorification of the notion of a group, which is a Frobenius category. Don't ask me details about this, but I heard at least that this is a good framework to look at categorifications of group actions where so yeah, if you have a group, its representations will be a Frobenius category, I believe. And then
Tanaka category. Tanaka.
Yes, but is it not also Frobenius? I don't know. I'm also only telling you what I heard from someone else who's studying this. But Yeah, there's many different things you can categorify, many different ways actually. I mean, categorification is somehow a mathematical principle where we go from
Right.
first numbers to vector spaces, and then maybe from vector spaces to categories. But yeah, so there's many examples. But in every case, it's somehow an interesting question of how you categorify.
Right. And it seems that there is no unique categorization. There are, as you mentioned, uh, two different categorizations in
Yeah,
one example that you gave. Yeah.
right. Yes. Yeah. So sometimes it happens that well, so if you look at the product and the co-product totalization, things become a bit more complicated, or there are different versions of totalizations which do not exist in the classical setup. Yes.
Oh, thank you. Any questions or comments? So then,
Just to confirm,
yeah.
maybe one last question. You said that you can define totalization on any bicomplex, like not just the squares, but if I had a bicomplex, doubly graded complex, any you can define totalization. If you
Mhm.
saw which one you choose, like always you have to choose the same product one, or so
Yeah, I
what is
think so.
Mhm.
So let's say we're in a bounded complex, but otherwise, I mean, how would you do it? You would let me draw a picture, but I think it's essentially what you would expect. So if you have something here, um, you just sum over the diagonals, and then you would glue these two categories along this one.
Mhm.
So these are glued with this one, these are glued with this one, these are glued with this one, and somehow um, yeah, there's a way to, yeah, essentially, I mean, you need to specify the gluing data of any categories, and basically the gluing data is this one will not be glued to this one. So we have maybe 1, 2, and 3. There's no gluing between data between 1 and 3, but the gluing data involves 1 and 2 and 2 and 3. And then you can just, yeah, this certainly extends this definition. But you need to say in every square that you're either gluing using the top left or using the bottom right. So either product or co-product totalization. You can't mix the, well, I wouldn't know how to mix the two, because you then in the end have to check that what you get is a chain complex. And yeah, there you would use that, I think.
Okay, thank you. Thank you.
Yeah, you're welcome.
So if there is no more questions or comments, so let's thank our speaker once more. And
Thanks for listening to my talk.
oh, I mean, we really enjoyed your talk, Merlin. I hope in future you will visit Turkey and we will
Yeah,
see each other face to face. Yeah.
yeah.
And have a nice time in Paris, I
Thank
mean.
you.
So, our next speaker will be 2 weeks from now. Uh, Felix from Roboton from well, he's at Max Planck now, former student of Carlos Simpson. He will be speaking on infinity omega categories as far as I remember. So we will see each other hopefully 2 weeks from now. Yeah. Thank you very much. Yeah. Bye bye. See you all later. Bye.
Bye. Bye, everyone.